Here's an interesting physics problem. Given these equations, can you find the pair of functions that satisfies them? This may not seem like a physics problem at first glance, but this formula returns the tangential and radial acceleration for a body using its angular and radial position functions as input. Now, it might just be a skill issue, but this formula really confused me when I first saw it. Why wouldn't acceleration in the angular direction just equal angular acceleration? For that matter, here's the equation relating velocity to polar positions. Why is the velocity in the angular tangential direction equal to r times angular velocity instead of just angular velocity? Well, the answer is actually pretty simple. Tangential velocity is not the same as angular velocity in a very fundamental way. Angular velocity of a point can stay the same when its distance from the origin is changed. But a particle with angular velocity 1 radian per second, 5 meters away from the origin, is clearly moving a lot faster than a particle with the same angular velocity 1 meter away from the origin. As a result, velocity in the angular direction, or tangential velocity, is not equivalent to angular velocity, with radians covered per time. The units provide a clue to this fundamental difference, but we humans are visual creatures, so the distinction is clearest when illustrated in a diagram like this. Similar logic applies to acceleration. If we make a radius and angular velocity constant, so the particle moves in a circle at constant speed, we get our acceleration in the radial direction to be negative radius times angular velocity squared, which makes sense when we consider there has to be some acceleration forcing the particle to move circularly, even if the radial acceleration, or change in radius, is zero. That was kind of a tangent, just like velocity in circular motion, but I want to make sure you understood these equations. At first, this problem seems like it can only be solved purely mathematically, but that sounds like a nightmare. No, there's a much neater way, using the mysterious quantity of angular momentum. And by solving this problem, we can gain a deeper understanding of not only polar coordinates, but angular momentum itself. Let's use the world's most high-end graphing software, Desmos. Consider a particle of mass 1. Set the particle's initial position to 10, 0, and set its velocity to 0, 5. This means that the particle's position, as a function of time, is 10, 5t. Unsurprisingly, the particle's momentum is conserved, staying at 0, 5. But what about angular momentum? It's calculated as position cross momentum, but what even is a cross product? The cross product has a scary looking formula, but is conceptually quite simple. Two vectors crossed returns a new perpendicular vector with magnitude AB sine theta, theta being the angle between them. However, we're working with vectors on a single 2D plane. As a result, our cross product points in the z-axis and has an x and y value of 0, so it can be represented as a single number. And the cross product's magnitude has a second formula. It's equal to the area of the parallelogram bounded by the vectors. This is huge. Since angular momentum is position cross momentum, angular momentum is basically just how much area does the particle sweep while moving. Angular momentum is zero when a particle moves parallel to its position, and is maximized when the motion is perpendicular to position. This also explains the dependence on our choice of origin. If we shift the origin, the sweep changes with it. Looking at our particle, it's clear that the initial angular momentum is just 5 times 10 equals 50. And as the position vector changes, the area of the parallelogram stays conserved. Thus, angular momentum is conserved. If we move the origin to where 10, 0 was, angular momentum becomes 0. Angular momentum is inherently dependent on whatever the chosen origin is. Now that we understand angular momentum, let's look at where it fits in the wider picture of rotational Newtonian mechanics. And we'll do that with the momentum master chart. Let's take a tour of this bad boy, shall we? Here's the momentums, angular momentum and regular momentum. They're bridged by the fact that momentum cross position is angular momentum. Now, let's look at their secondary formulations. Just like momentum is mass times velocity, angular momentum is moment of inertia times angular velocity. What's moment of inertia? Who knows? But it's basically the rotational analog of mass. And for the particle, it equals m times r squared, where m is mass and r is the distance from the axis of rotation, or in our case, the origin. The time derivative of momentum is force, and in the same way, time derivative of angular momentum is torque. And wouldn't you know it, force cross position is torque. In other words, torque is the sweeping area of force on position, changing angular velocity the most when the force is perpendicular to position. Finally, at the bottom is the formulas for force and torque. Here's where you have to be careful. These only apply if the mass/moment of inertia is constant. That's reasonable for mass, but moment of inertia depends on position, and thus is only constant in certain situations. However, it still shows the relationship between force and torque, momentum and angular momentum. It's a common line, but it bears repeating. Angular momentum and torque are Newton's laws applied to rotations. Using these formulas, we can actually find the angular velocity of our particle even though it's moving linearly. L equals I times omega, so we just need to find the particle's moment of inertia, or mr squared. Conveniently, that becomes 10 squared plus 5t squared, which is equal to 100 plus 25t squared. So our angular velocity is 50 over 100 plus 25t squared, which simplifies to 2 over 4 plus t squared. Integrated, we get an angle of arctan t over 2. This means the angle of a particle at 10, 0 moving upwards at 5 units per second is arctan t over 2 radians. This again shows the importance of origins when handling rotations. If we slid the origin closer to the particle, the angle of the particle at any given moment would have been slightly different. As for the radius function, it's just square root of 100 plus 25t squared. So our final position function in polar form is square root 100 plus 25t squared, comma, arctan t over 2. And here's where those equations from the beginning of the video come in. If what we've discussed up until now has been correct, these two functions should be non-trivial solutions to those equations. Since our body has constant momentum and angular momentum, there's no force or torque, which means there's no acceleration. So here's the moment of inertia, I mean truth. Let's check if the overall acceleration is zero, given these two functions.